The title of the paper I'm presenting is Energy Dissipation in General-Purpose Microprocessors. The paper shows that a processor's energy consumption is closely related to its performance, which leads to the selection of the energy delay product as a comparative metric for different processors. In the paper, methods are explored to reduce energy consumption without compromising performance and to minimize delay by exploiting instruction-level parallelism. The results show that careful design can reduce energy dissipation by nearly 25%, while pipelining can yield about 2 times improvement. However, superscalar does not lead to further enhancement in the energy delay product due to the associated overhead offsetting the performance gains. Overall, the efficiency of processors is projected to rely more on the technology employed and the algorithms chosen by programmers rather than the microarchitecture. In the introduction, the paper highlights the diversity in available processors, ranging from low-power machines with modest performance to high-performance processors with substantial power dissipation. And since, quote, for processors, power and performance seem to be strongly correlated, end of quote, the paper then suggests that processor energy and delay should be considered simultaneously. The main sections of the paper are as follows. First, the paper discusses the relationship between the power and delay of CMOS technology employed in processors, emphasizing the trade-off between increased delay and reduced energy. It then introduces the energy delay product as a superior metric for design comparison. The next section then explores the lower bounds for energy and energy delay product for different processors, examining ideal machines as well as real processors. In the final section, the paper states that the energy consumption of these real machines is within a factor of 2 from the ideal machine. This is after conventional optimizations. It suggests that further reducing power overhead will be challenging. In this section, the paper compares various metrics such as power, energy, and energy delay product across different processors. The authors argue that simply reducing power or energy per instruction may not necessarily improve the overall efficiency of the processor, as it could lead to decreased performance. The authors then propose that the energy delay product is a more comprehensive metric for evaluating processor efficiency, as it considers both energy consumption and performance. It is also highlighted that to enhance the energy delay product of the processor, designers should focus on increasing performance or reducing energy dissipation without compromising the other factor. The impact of the scaling factor because of technology is also discussed, and it is noted that the energy efficiency as indicated by the energy delay product becomes remarkably similar when scaled by technology. This is demonstrated by the last row of the table on the right. The next section of the paper aims to investigate the lower bounds on energy and energy delay by investigating 3 idealized machines. The analysis of energy is limited to reading and writing memories, clocking storage elements, and essential energy dissipation. The energy costs of computation and communication within the data path are assumed to be 0. Speculative operations and unwanted transitions are also excluded. In the analysis, all processors fundamentally perform the same operations of fetching instructions from a cache, using that information to determine which operands to fetch from the register file, and then either operate on this data or use it to generate an address to fetch from the data cache, and finally store the result. The 3 idealized machines are based on an unpipelined processor, a simple pipelined RISC processor, and a superscalar processor. The unpipelined processor uses a simple state machine to fetch instructions, operands, perform operations, and store results. The energy consumption for this model is based on the assumption that control transfer instructions take 2 cycles, ALU operations take 3 cycles, and cache operations take 4 cycles. The energy dissipation during clocking is not considered, but the energy required for reading and writing caches and the register file is taken into account. This implementation is expected to have the lowest average energy per instruction, but it suffers from relatively poor performance and a high energy delay product due to not exploiting available parallelism. For better performance, the paper introduces a pipelined processor that exploits instruction-level parallelism to execute more than one instruction concurrently. In addition to reading and writing memories, the energy delay product of this model is also affected by pipelining and additional energy required for clocking the latches. The paper also discusses the ideal superscalar processor capable of executing a maximum of 2 instructions per cycle. This processor uses an aggressive static scheduler from Torch and assumes conditional execution of instructions as directed by the compiler. The energy delay product difference between this model and the previous one is attributed to its ability to execute 2 instructions in parallel. The comparison of energy and energy delay product in this section reveals insights into the performance and energy efficiency of different processor architectures. All energy values in this section are normalized to the value of the superscalar processor. It is observed that the unpipelined machine exhibits the lowest energy dissipation, while the superscalar machine demonstrates the highest. Conversely, the execution time showcases a reversed pattern, with the superscalar processor delivering the highest performance and the unpipelined machine showing the lowest. The energy delay product is also examined, with pipelining significantly boosting performance at a minimal energy cost, resulting in nearly a 2-fold improvement in energy delay product. On the other hand, superscalar provides only a marginal enhancement in energy delay product with a higher energy cost. The limitation of a processor with a wider parallel issue is that while increasing the peak issue rate boosts performance, it also escalates the energy of every operation, particularly memory fetches and clocks. Additionally, the speed-up of the superscalar processor is constrained by Amdahl's law, as the stall time becomes a larger fraction of the total execution time, which limits the decrease in energy delay product. Also, the overhead in a superscalar machine surpasses that of a simple machine and outweighs the modest gain in energy delay product from parallelism. In the section about current implementations, the authors maintain that simple optimizations can lead to a significant reduction in energy dissipation in real processors. These optimizations do not heavily impact the critical path, but result in a considerable decrease in energy waste. 2 specific processor models are compared. First is the simple RISC processor, which is noted for its similarity to the original MIPS R3000, but with added on-chip caches. It features the same 5-stage pipeline as in the ideal machine. So it is very similar to the ideal pipeline machine, except that it counts for all the energy required to complete the instruction, and it also includes all the overhead associated with the architecture. The second processor is Torch, a statically scheduled 2-way superscalar processor, which also uses the same 5-stage pipeline. The processor includes a shadow state, which can buffer the results of those conditional instructions until they are committed. There are also measures to improve the code density, which keeps both data paths busy for programs that do not have enough parallelism. The paper uses Torch as an example due to its comparatively smaller overhead in contrast to an aggressively dynamically scheduled processor, which will have a higher energy per instruction but only equivalent performance. The section on energy optimizations discusses techniques for reducing energy consumption in different architectural features. The energy can be divided into overhead, which cannot be eliminated with design, and waste, which can be designed away. Within techniques that are used to reduce waste, clock gating can be used to eliminate transitions that should never have happened. Also, latches that are not in the main execution data path are qualified. As a result of clock gating, approximately 1/3 of the clock power and close to 15% of the total power could be saved. Also, the selective activation of macro cells and eliminating cache and register file accesses during machine stalls also save approximately 8% of the total power. The paper also stresses the importance of weighing power dissipation gains against the costs in complexity and cycle time. For example, the use of speculative operations, although common for improving performance, can consume extra energy if not carefully managed. The figure on the right shows energy differences when certain simple optimizations are disabled. And the authors state that while simple optimizations can save almost 20 to 25% of total power, Further gains might be harder to achieve due to the dissipation of energy in various different units. The next section examines the energy execution time and energy delay product of the ideal superscalar machine, the simple RISC machine, and torch. It appears that torch requires the most energy to execute a program, and closely followed by the RISC processor. The difference in energy between the ideal machine and torch represents potential future improvements. In the second figure, the total execution time for torch and the ideal superscalar machine is the same, as they have identical execution models. Also, the superscalar processors exhibit a 35% speedup compared to the single-issue machine. Finally, in the comparison of energy delay product for the three machines, torch and the simple RISC processor demonstrate similar efficiency. The superscalar issue provides a small gain in performance. However, it also increases the energy cost of all instructions, resulting in no significant improvement in the energy delay product. The ideal superscalar processor is actually twice as efficient as the real machine. In a detailed energy breakdown, the authors divided the energy dissipation into four categories, the first being energy dissipated in reading and writing memories, such as caches and the register file. The second category includes energy dissipated in the clock network. The third includes energy dissipated in global interconnect nodes, and the fourth category comprises energy dissipated through other channels. So the energy breakdown for 3 of the 5 simulated machines is shown in the figure, which has been normalized to the total energy dissipation of the torch processor. It can be observed that the energy dissipated in the on-chip memories is almost the same in the ideal machines as in the implementations, which means the reduction of unnecessary cache accesses is successful. The authors observe that the clock power in the real machine is slightly higher because there is a large amount of states that they did not consider in the ideal machines. Global interconnect and computation each represent about 15% of the total energy, the two categories that are not considered in the ideal machine. The authors consider it important that further improvements in the energy delay product will be challenging to achieve, as the energy is dissipated in many small units, and that significant reduction in energy would require reducing the energy of many of these small units. In conclusion, this paper highlights the relationship between processor performance and energy consumption. It shows that processors across a wide range of performance levels exhibit similar energy delay products. This similarity is from two main factors. First, all processors perform similar functions, and key operations such as accessing on-chip memories and clocking constitute a significant fraction of the total energy dissipation. Therefore, even doubling the energy dissipated in the combinational logic has only a minimal impact on overall energy dissipation. Secondly, pipelining is the primary architectural feature that significantly enhances performance at a low energy cost, and other architectural features do not substantially alter the energy delay product. Since most processors in use today are pipelined, it is expected that they would all exhibit a similar energy delay product. Additionally, the paper points out that while it is feasible to reduce energy requirement through careful design, such optimizations would provide only a one-time improvement. The reason is as follows. Employing straightforward optimizations can indeed achieve a reduction in energy consumption by approximately 25%. However, achieving further improvements would necessitate more advanced and sophisticated optimizations, as the remaining energy is dissipated in numerous small units, none of which individually account for a substantial portion of the total energy dissipation.